So first of all, let's welcome Professor Jonathan Howe to join this seminar. Professor Jonathan Howe is the Richard McLaurin Professor of Aeronautics and Astronautics at the Massachusetts Institute of Technology. He received the undergrad degree from the University of Toronto and his master and PhD degree from MIT in 1919 and 1993. He's a fellow of the IEEE and the American Institute of Aeronautics and Astronautics, and he was elected to the National Academy of Engineering in 2021. Dr. Howe's research focuses on robust planning and learning under uncertainty with an emphasis on multi-agent systems. And his work has been recognized with multiple awards, including the 2020 IEEE CSS Distinguished Member Award, the 2020 AIAA Intelligent Systems Award, and a long list of countless other awards. So today he will tell us about learning-based planning and control opportunities and challenges. So without further ado, let's welcome Professor Jonathan Howe. And if you have any questions, feel free to type in the chat or directly chime in to ask a question. Thanks and welcome.
Great, thank you very much for the introduction. Yeah, my name is John Howe, and I'll be talking to you about some work here I'll be doing, have been doing with a lot of different collaborators, and you'll see their names along the way. I don't know if you provide slides. There's a lot of references that are indicated in the slides that are most useful if you have access to the back, which I'm not going to show, but they will be, hopefully I can provide the slides to you so you'll get a chance to click on them if you need to. Anyway, thanks for inviting me to give the talk today. And I'd like to talk to you about sort of, like as the title says, learning-based planning control, opportunities and challenges. And so we'll be talking a bit about some of the technologies that we've been doing, but really sort of trying to identify key things that need to get addressed and things that perhaps we've done well and things that need to be done even better. But again, for those that don't know, my background is sort of, traditional planning control. I sort of came out of the H infinity mu sort of synthesis time frame that some in the audience might remember. Others perhaps I've never even heard of that, but we'll see how that connects to the things I'm going to talk about here. But as I indicate, there's a key role for traditional planning control in finding some of the globally optimal policies that we're ultimately looking for in this learning and planning and learning work. But as many of you begin to recognize or have seen in some of the work you might have done, that some of the systems are just very difficult or impossible to model from first principles, and or they result in very complex models, which themselves lead to very complex control systems that we would then have to try to implement. Of course, there is the curse of dimensionality in dynamic programming that you will learn about in your sort of classwork. And so when you go out into the field and try to implement this type of stuff, you begin to realize the limitations of those classic type techniques. And or when you get to the real world, you just realize you get poor performance when things seem to be working great in MATLAB and seemed okay experimentally, but then sort of fell apart. And so over the years, this is under the guise of sort of different names, but it's sort of motivated, working more directly with the system and or the data from it. And so here I'll be talking more about the machine learning and reinforcement learning, but obviously I pay homage to the fact that many of the similar techniques I'll be describing have also been thought about within the context of system ID and adaptive control. And there's quite a few papers out there on linking these various technologies together. But ultimately the point here is to be working with that system, with that data, and then thinking about either policies and or models and how we would adapt them and learn from them, both for single agent systems and multiple agent systems. Now, again, a lot of this over the past, decade or so now has sort of really come to the fore in part because of the changes that occurred around the time of 2011. And there's a picture here, so the classic, step change in the capability of the image classification that occurred around 2011, 2012. And that led to a lot of serious interest in the deep neural networks. That work obviously been going on for many years, if not decades prior to that. But the sort of step change in that type of performance led to what is now often described as sort of superhuman performance in many of the tasks that can be done with these CNNs and DNNs and things of that nature, well beyond sort of what was capable before. And so that sort of led to this revolution in the past decade in terms of people beginning to think about how these neural nets can be applied within the context of control systems, which includes many elements. Obviously, there's modeling, perception, navigation, control, and other aspects. And you'll see me talk about all of those as we go along. Okay. And if there's any problems with the audio or anything like that, please just wave your hand or something. As you know, with these types of systems, you tend to get tunnel focused in on the thing you're looking at. So I can't really tell if there's a problem. Now, the thing is that as this work has gone on, and the learning-based algorithms are actually now at the point of being state-of-the-art in many of these complex robotic perception and motion planning tasks. And I have links to the videos here. I've learned that showing videos over Zoom is quite challenging, in part because of the latency involved. So I won't play them here, but hopefully you've seen some of these before. I mean, all of them are showing, sort of what I would describe as this approaching superhuman type performance. But in particular, one of the things that's interesting about them is that they tend to outperform the traditional model-based techniques, in part because models themselves tend to be abstractions. And that furthermore, they often require far less domain knowledge and or expertise, which again, if you don't have that domain knowledge or expertise, is actually beneficial, because then you can get into an area and get into a field and start generating quite high levels of performance without necessarily having to invest a lot of money. Now, as you can imagine, though, there's quite a few challenges that still remain, which is part of the reason we're here. If you're interested in sort of a deeper dive into what some of these challenges are, I point you to some of these sort of various locations you might want to take a look. So the CSS webpage itself has a very significant set of these grand challenges for control, verification, validation, and certification. A key piece of what I'll talk about here is just one of the ones they talk about, but there's a whole bunch of them like that. So if you've not seen that, the work by Tariq and Anu, please go take a look at that. And it's on the CSS page. In the past year or so, I think there's been one of a series of articles that have come out, such as this middle one here, just thinking about sort of these, not just, systems of control for the sake of control, but, within the context of, as it says here, humanity. So it's pretty broad scope, and they have some very interesting set of discussions of technologies, both adaptive control and various types of control, and how they might apply to addressing those issues. So that's a great thing to look at. And then obviously the latest in the internet sort of robotics type roadmap for robotics that Henrik Christensen has been developing with a whole bunch of other people. So that gives you sort of a very broad scope of the types of things that people are interested in these areas. When I take a look at that, I sort of come away with a set of significant challenges, in particular having to do with machine learning and reinforcement learning. The first obviously having to do with complexity, and there's many different types of measures of complexity, but often the issues are dealing with sample complexity and computational complexity, sort of highlighted here. And these are the two main axes that we tend to struggle with, is how much data do we need? And then if you give me all this data that I tend to want, how do I deal with the computational challenge of actually getting an answer out of this thing? Then there's going to be a safe learning issue, which is just sort of ultimately this question of the guarantees that one might get out of a learning system like this when you actually put it in a controller or a control system. What can you guarantee? What can you verify? And how safe is this whole thing going to be when you actually start executing it? And then, as indicated in the introduction, much of my career is I've spent time looking at the multi-agent systems and learning. And so when you think about multi-agent learning, now you're talking about agents possibly learning from each other, learning in teams, learning perhaps against each other in the sense of adversaries. But here you're thinking about issues in terms of scaling, and then also sort of architectural design. How does one actually go about doing this learning process anyway? So if possible, in the time I have left, I'll try to touch on sort of some ideas and thoughts in each of these areas. Like I say, it's these are pretty broad topics, and it's a lot of ground to cover. So if I leave anybody out and don't touch on things, then it'd be great to have a conversation about that at the end, perhaps. So in terms of complexity, then, one of the things we've been struggling with here is just how much data is often required. And so there's a question of, with that amount of data, you typically end up using a simulator, which is great for creating perhaps lots of those simulation data points. On the other hand, there's a question of, is that simulation data actually sort of, how do you make the transition from simulated world to real world? And so there's a bunch of issues that we'll touch on here, but one of them have to do with just the fact that even collecting data in the real world can be expensive. And so anytime you're doing this with experiments and there's a possibility the thing can break, and or you just have to reserve field space, That's a difficult thing and expensive thing to do. So the question is, how do you sort of do the transition between, say, low fidelity sort of abstract models all the way up to real world experiments? Of course, there's other questions where, yes, you can get data from human sort of demonstrations and robots can follow you, but anytime humans are involved in experiments, say there's a safety concern, and B, it's just a very time consuming and difficult process. And as I mentioned, this sort of sim to real transition is something that's working in a simulation has its great benefits, but if they're not representative of the real world, what's going to happen when the robot gets there, and how do you make that transfer? So there's a bunch of questions here that have to be addressed as well. So one of the things we started looking at in this sort of dealing with the model complexity question was sort of ended up being what we call the multi-fidelity RL, reinforcement learning. And as I said at the beginning, I mean, there's obviously a role for using, when I say simple models here, I'm really thinking more of the abstracted, where you sort of have to carve out, all the sort of nuances and cut them off, and then just work with sort of the cleaner, sort of more basic kinematics and dynamics of the system, including what you can to develop the controllers. From that, you're going to get sort of, say the traditional, LKG H infinity type of controller you're going to design, and this will be the thing you want to go implement. If you're lucky, you typically, you might then have a more complex simulation in which you can begin to experiment and see how well that works. But the point is, as you go from simple to complex and then ultimately the real world, you're getting more accurate data because it's more representative of what you care about. On the other hand, cost typically goes way up in terms of effort required and computation time required. So ultimately, what you'd like to be able to do is to refine the learning-based methods. So when you go from simple to sort of complex and start learning about how to do things better, you'd like to be able to refine those learning-based controllers on those more complex simulations, in part then to think about how one goes into the real world and what one does when you get there. And so one of the things we were looking at was not just the traditional sort of one-way transfer where you sort of think about learning in a more complex simulation and then thinking about how to transition that into the real world experiments, but also how you get bi-directional transfer, where you're thinking about bringing the information from the real world back to the complex simulation, thinking about what limitations and issues it perhaps points out in the simulation that you have, and then ultimately perhaps even going back to the abstract model that you had developed and also thinking about what limitations might exist there as well. So that bidirectional transfer then you're using as a way to try to cut down the number of samples you actually need on the real world to understand what is actually going on, where the real differences are and what the real issues are. So again, you're looking at the sort of forward model as a way to initialize the policy and exploration in the real world. And the reverse transfer then is of the observed data is to sort of evaluate the quality and performance of the learned policy in this perhaps more complex simulation you're doing. Ultimately, this boils down to, or a key part of what this boils down to, is a design of experiments. And you're actually beginning to think about, in the forward transfer sense, if I get to the real world, what experiments do I really need to do that are going to be the most constructive in terms of figuring out what's wrong with what the complex simulation is? And then when I get that data, how do I bring it back in terms of both, not just model update, but also policy update? And also in terms of learning, how do I do incremental learning based on that one or two pieces of real world data that I collected? And so there are some key issues there about how one goes about integrating that type of that full process. Mark Cutler, the student working on it, was just super interested in doing some drifting. So again, this predates some of the work that I think more recently, anyway, at Stanford, that they've done drifting cars, and very impressive work there. But at the time we were doing this, what we were interested in was sort of driving an RC car around on a dirt floor, or a dirty floor, but that way it's tiled, not particularly clean. The net result is you have really poor understanding of the sort of the wheel parameters, and it turns out within this field is the tire parameters actually called magic parameters in the model, and it's actually what they're called, and in part because they do magical things. If you get them right, yeah, you get the right model, but most of the time you have no idea what they are, and you really just don't understand the traction that this car is actually going to get. So ultimately, you want to drive this thing in donuts. That's what he was trying to do. It requires you to effectively drive just like the guy up here, as sort of a skidding around the corner like this. Again, we're using sort of Vicon and onboard sensing and things like that to try to cut some corners and get to an end result in terms of what we can do in terms of actual performance. But the net result was thinking about these different level fidelity models that we can create, and how we learn a policy or develop a policy and then learn and revise that policy in the more complex models. It's similar to the picture I described in the previous page. So ultimately what you get then is something where, if you went off and designed a sort of optimal controller based on an abstract model and what you think the magic parameter is going to be, you go and implement it in the real world and you realize it just doesn't work that well, which is sort of what this picture says. It was the optimal control implemented on the sim. But the point is that that then becomes a good learning initial condition for the sort of learn trajectory within that more complex simulation environment. And the thing is doing something that looks more like a donut that you would expect. And then when you dive into the details of what the differences are, they're subtle, but there's differences in terms of delta here, which is the stirring angle for the wheel. And you'll see when you see the video just how high frequency that stirring input is to get this thing to actually do a donut well. So again, you would sort of learn something new in the sim environment. You think life is great. You then go off into the real world and you sort of turn it on the car. And the net result is that when you take that result, put it on the real car, you get this jumble mess over here. And the thing was basically just doing nothing that looked like a donut at all. And it was just a mess. But again, that becomes a good initial guess for determining how to do learning in the real car. And again, the bidirectional transfer sort of described in more detail in Mark's thesis work, but the net result is that then you can learn from that how to effectively drive donuts. And again, there are key differences in the way the control action has been learned between the result on the sim and the result in the real world. So as you might expect. So hopefully this comes across, but this is sort of, as with a lot of learning type videos of this type, you can't really see the learning in real time. I mean, it's, so this is sort of, this is like a cooking show version where we're sort of stepping through various steps in the process. This is us now having learned the policy, and we're sort of demonstrating that we can actually handle various levels of traction, in part because I told Mark I was going to come in and throw dirt on the ground, and so he did it anyway. And so he just put rock salt down and just demonstrated that even though he doesn't really know what the traction, the parameters are, he can actually handle and do donuts in that environment quite well. And this is just showing that we can actually do donuts around objects. And then I think in the next video, he actually started moving the object and showing that you could do donuts around it. And again, in a motion capture world where you have access to a lot of knowledge, it's not that hard. Here you see, though, the amount of wheel input and how high frequency that is, the amount of effort that's required to do this. Again, this is driving and translating and doing donuts at the same time. Again, it's sort of, just a demonstration of something to highlight a particular case where when we don't know the parameters particularly well, we can still actually learn how to drive in this type of environment. So it also shows you how dirty the floors are in my lab. So that's one aspect of that, and that's thinking about multi-fidelity. Another thing that tends to show up, and you'll see this discussed a lot in the field, is meta learning, where again, you're dealing with this question of sample complexity. And the idea is that, it's unlikely you're ever going to see everything that you ever want this agent to be able to do. So sort of notionally, the figure up here is I show it how to do lots of stuff, and then yet you ask me to do another thing. And it's like, okay, I want to take an agent that's good at all these things, and now you ask it, what can you learn how to figure skate? And so the point is that, in the real world, it's always likely you're going to get asked to do one more thing other than what you learned about. And the question is, can you develop an adaptable policy that can actually figure out how to transition into this new task, even though you don't necessarily know what that new task was ahead of time? And again, what you're learning here, and this is a lot like doing a robust learning exercise, what you're trying to do is to develop a policy that is easily adapted. You don't necessarily know what it needs to adapt to, but you're trying to enhance its ability to adapt to things by essentially embedding into it, not just data, but what's effectively called meta-trained data, another component. And that essentially what you're doing here is thinking about other things that you'd like to be able to be good at, and then possibly thinking about, effectively how to create an ability to adapt to those. You're not necessarily training based on data from them, but you're sort of at least anticipating the existence of new tasks or system perturbations during execution. So sounds great as a strategy, and is often used in a lot of the robust control work that we do and this is robust learning, but it's similar in context. But a lot of the issues here and the challenge in this particular work then is that the effective learning process, A, is computationally demanding, and B, it requires you figure out that model. What is you as a designer, what is your vision for what other things should you be aware of that the system may not be learning about specifically, but is anticipating the existence of. And Obviously, the result is going to depend to a large extent on this model. What else are you anticipating might exist? And this often occurs in these types of systems. So again, this is not just relying on adaptation when you see the existence of it. You're sort of pre-anticipating the existence of this in such a way that you can cut down the amount of data you need to do the adaptation when it actually has to happen. And so that's beneficial when you get it right. The question is, how do you get it right? How do you make that anticipation? So again, that's part of the challenge here in this particular aspect of this work. This primarily coming out of Chelsea Finn and Sergey Levine's group, I guess, and Peter Abil as well. And again, I won't show the video, but they sort of show a robot here where I think there's 6 legs. One of them falls off, or they broke it off. But the net result is, compared to the other 2 techniques, again, the robot's supposed to walk up and down this line, and this one does a great job of doing so. So it seems to work well, but again, requires you to be able to anticipate. In this particular case, I think we're able to anticipate any of the legs falling off. But the question is, what if more stuff broke than simply that? And that's the issue here in this type of work. So I mentioned before about learning sort of sim to real transfer. And again, there's a lot of work here. And again, this is other work coming out of Peter Abil's group and Sergey Levine's group in terms of CAD2 RL, which is thinking about that transition. And domain randomization is another aspect of robust learning that shows up here in terms of thinking about these types of sort of perturbations of the simulation environment that can be embedded into the learning process in such a way you're now robustifying the policy you create. So when it gets to the real world, it's less surprised by differences. But one of the things that's also becoming clear over the past couple of years is just how great these simulation environments, things like AirSim and Flight Goggles coming out of here at MIT with Surtash's group, how great these have become. They're great at providing almost sort of video quality simulation environments to work in. So it sort of cuts down the hardness of making this transition from simulation to real world. The problem is, if you've used them, is then you get into runtime issues, which is now it's a question of, the quality is good when I'm working within them, but they're very hard to run in terms of time. And so it's a question of ultimately a trade-off between quality and runtime that one has to make when using these types of techniques. I will make a comment, though, that we've often struggled with this, that despite realistic sims and sensors and vehicles, it's still difficult to sort of anticipate the response of other agents. And so one of the things we've been looking at, and you've probably seen us do work in the past, is dealing with robots interacting with humans. And the challenge there is a situation where, again, you have humans in the loop, so everything essentially has to run at runtime. There's no or real time. You can't sort of speed it up. Plus, there's a safety issue. You can't sort of have robots just driving around humans, checking out your safety code and hope it works, because they tend to get whacked in the shins, and they're not don't like that a whole lot in this safety concern. So one of the things we're actually setting up here was sort of a whole situation where the humans essentially walking around with VR goggles on, which isn't entirely natural, I'll admit. On the other hand, what it does enable us to do is to hallucinate a robot in that environment that the human sees. And so what you're seeing here in this video is what the human would see. So now you get to actually see the human response to the robot. It's just that the robot is fake. And so there's no collision problem. It's just that you actually get to measure the response of the human, provided you can make it seem realistic enough. So again, it's a way to try to create that data set when you actually have humans in the loop. And I don't know how to speed this up, which is, again, one of the issues. On the other hand, this is a way to address part of the safety issue. So again, the sim to real gap is reducing, but it's still there, and it's still time consuming, and something to think really hard about in terms of these large data sets. And often when you see machine learning plots, you look at the x-axis of the graph, and they're typically in millions of samples. And the point is, if there's anything like a human involved, you're going to get ones of samples, possibly tens, not millions. So it's a question of how does one handle that type of sort of data disparity in terms of needs and actual capability. And that's sort of this element down here. So being able to do training with much less data, but the question is, ultimately, is how representative does that data become of the real world? And so, as I mentioned before, sort of part of that is the design of experiments, or really thinking very carefully about, and sort of essentially poking holes in your capability within the simulation environment you have to really think about what experiments I should do in the real world so I can maximize the information gain from anything that is done there. And like I said, the multi-fidelity type techniques are sort of a key element of that, I believe, as well. But ultimately here, I think that, making sure we are able to avoid just black box learning techniques and really bring physics-based modeling and constraints into these types of learning techniques is ultimately, I mean, again, when I was working on system identification many, many decades ago, it sort of became clear that, the sort of black box system ID, but if you can bring in some type of modeling frameworks and constraints, dynamics constraints, and end up more of a gray box type learning system identification, they tend to be, that grounding then tended to create much better results that had better transferability. And I imagine the same thing ultimately is going to end up happening here when we can start bringing in sort of the same types of modeling and constraints into our machine learning techniques as well. So anyway, things to think about for future directions. The other topic I wanted to mention here, touch on is certification. Again, a lot of the issues we're dealing with here when you're talking about feedback control systems is obviously the issue is that the types of decisions you're making can have major safety implications. And there's a picture here showing of someone just put something on the ground, which ended up taking a system, and I'll let you guess as to which one this is, make a pretty radical change in the actual driving decisions as it was moving forward, which was not good. And of course, there's the unfortunate situation that occurred with the Uber car and in Tempe, and so there are situations of that type where you start thinking about these safety critical domains. And the point is, you want to be very careful when you're starting to think about reinforcement learning, machine learning, and the learning you're doing for them, and how you're going to implement them in the real world. And so, ultimately, similar to what we were just describing, the point is it may work well in the simulator it was trained in, but how will it transfer to the real world, in particular with noise? How well do we know that it's going to satisfy things like safety constraints in terms of thou shalt not hit this? So these are the types of questions that this work is particularly interested in. We ran into this here where, at the time we were doing CAD RL, which is our version of collision avoidance with deep reinforcement learning. Again, we're trying to learn how to drive in an environment with lots of moving objects, pedestrians in this case. There's no real safety concern here because we're walking behind this thing with a giant red button. On the other hand, there were a lot of environments and situations here where we could get performance improvements. But when you start thinking about safety and certification in terms of the future deployment of this, and if you actually wanted to use this in other types of environments, what could you say about how well this is going to work? And so it's not just a performance question anymore. It gets into these other questions here in terms of safety and certification. And this is essentially what happened with my group. Was a student who worked on this and sort of published papers from the perspective of, look how great this is. You bring the next student along and they start asking questions like, yeah, but what about safety and certification? Can I be confident I can deploy this on larger vehicles? Now, again, these are not new questions. I mean, neural nets go back, the 60s. I remember them back in the 90s. And again, this is probably dating myself, but I remember when they were all the rage back then. And so the point then being that at that time, that was mostly thinking about neural nets for control systems. What's a little bit different now is we're thinking about these deep neural nets that I mentioned earlier, being used for the perception, planning, control, and modeling. And again, I'm not saying it wasn't the case back then, but it certainly is the case now. And so there's many different boxes within the control system path, and sort of often find deep neural nets, and at least one, if not more than one, of these boxes being used. On top of all that, there's sort of the sort of discovery, back in the early, again, about a decade ago, of just how easy it was in terms of these small perturbations that can be made to these pictures. And then you start getting, completely different classifications coming out of it. And I'm sure you've all seen the, panda plus epsilon times whatever this is, all of a sudden becomes a gibbon. And, you've seen the classic, stop sign that's no longer a stop sign, and other things in terms of the the turtle with a stop sign on it, is it a stop sign or a turtle? And so these are the types of questions that people have been thinking about since then, and it sort of motivated a new field in sort of computer vision and machine learning communities on the neural network verification. And again, there's a whole spectrum of different solutions that people have been looking at here, all the way from sort of the more complicated, exact, and possibly slower methods down to the ones that are focused on fast and perhaps more real time in terms of their implementation. We'll be talking about techniques that sort of fit sort of somewhat in the middle of this category here, somewhere in between the QP and LP, and we'll talk about that in a second. So again, in this work, ultimately, we have to think about both analysis and synthesis. And for me, this is sort of a lot like going back to thinking about the control field as I understood it back in the 80s and 90s. And this is a book from a textbook that I used as a grad student. This is sort of figure 1.1, a picture of the history of control. You got the classic control guy, you've got the sort of the nerdy sort of modern control guy, thinks that LKG is a solution to all problems. And then, of course, was the ugly reality of what happened after that, which is the recognition that there were, with modeling errors and sort of errors in the assumptions about the noises, that the world was a lot more complicated than had been assumed, and by the techniques that were developed. And so this modern control, it then led to what I think now is a quite dated terminology in terms of postmodern. But ultimately, what this led to was a recognition of the need to be spending a lot of time thinking about analysis, thinking about synthesis, and in particular thinking about how do we model uncertainty, how do we capture the uncertainty in the problem, understand how that uncertainty propagates through the system, and then think about how we can sort of understand the uncertainty of the output and then begin to bound it. And that led to a lot of the work on H infinity and mu. And it was only recently that I think realized that the H infinity was actually here as a tattoo, and of course the mu is in the staff. So it's sort of a funny cartoon from many years ago. But again, it's for me, I see really a lot of analogies in this field and the thought processes that it's undergoing and what I had witnessed as a student and a postdoc at the time in the control field itself. So it's sort of interesting from that perspective. So a lot of things on this slide, not trying to go through everything here, but I'm just trying to make the distinction between what we're trying to do in terms of a control system versus what I think a lot of the field had been doing previously, which is thinking about these isolated neural nets. It's sort of, is this a dog, question? And there it's pretty clear how to evaluate dogness. We label a bunch of things. You say, oh, that's a dog, can this thing report dog? And so, there's a lot of progress in thinking about the types of things, ultimately people go from, say, the standard learning, which is trying to get the thing to work, all the way up to robust synthesis. And the point is, I wouldn't say this is necessarily easy, but it's easier and people have been thinking about it longer. And I think they've made a little bit more progress on the left side. Over here on the right, we're obviously thinking about neural nets now in the perception, planning, control, and other parts of the loop, and trying to understand the complexity or more complex situation over here. And I say more complex in part because it's not, here we're not just assessing whether or not it's a dog, right? We have to be assessing safety. And then ultimately this question is like, what does it mean for this feedback system to be safe, right? How do we actually evaluate safety of this thing? And so there's a lot of questions here about what that statement even means. And so I think less progress has been made. Progress has been made, but less progress. And I think as a result, there's a lot of room for future work here as well. So ultimately, what we're trying to do then is in this particular case, and I'll just talk to you a little bit about the work we've been looking at more recently. Again, you're thinking about, you have real world uncertainties and you have a neural net that represents something. It could be some type of a policy, or it could be some type of classifier. And you're just trying to estimate, if this uncertain thing went in, what's going to come out the other side. Seems relatively straightforward to realize the neural nets are very high dimensional and nonlinear. So some approximation is going to have to be in there, and it shouldn't be too conservative. And again, a lot of analogies to what went on back in the robust control era because of the similar types of nonlinearities that had to be captured, similar types of sort of questions about conservatism and things like that. And so the idea here was to actually begin to think about not just sort of a big uncertainty block. This is sort of two axes of uncertainty here. And we're thinking about partitioning that. The point when we do effectively try to do the same calculation for the uncertainty propagation, but we're doing it for smaller segmented chunks of the input space. And then the question then becomes one of, okay, great, but how does one actually do that segmentation? That's one question. The other then is how do you propagate any one of these uncertain blocks or segments through the neural net? And the question is, what does it look like on the other side? And so, again, if you just ran the system doing some type of Monte Carlo and just sort of randomly pick points over here, you end up with a little black blob sitting inside here, the dots. The sort of the outer bound of that is the red dashed line. And what we're trying to do is create an outer approximation of it. This is as tight as we can possibly get it. And what we're able to do through the partitioning, as you can see on the right-hand side here, the partition set is getting closer and closer outer bound to the red line. It's not perfect, but it's much tighter than it would have been. And so that's ultimately what we're trying to do, is develop a better estimate of the uncertainty set on the output side. And then the question is, what do you do with that type of thing? So one thing we were looking at was sort of this type of collision avoidance problem where you as the orange agent are thinking about where the blue agent might be. They're sort of normally the adversary. You're thinking about a policy or an action you might take based on a state action sort of value function. And so the question is, if this ends up being a neural net, how do you propagate the uncertainty in the adversarial state through that type of neural net? And so you could end up doing the sort of the more traditional type, it's safe, but ends up being conservative. If you end up going through the partition set, which is sort of ultimately what we ended up trying to do here, you can end up with something which, at least in this cartoon or this simulation, ends up being a much, it's also safe, but ends up being faster in terms of the completion of the maneuver itself. And so it's just a simple example of how that type of idea about thinking about the sort of the uncertainty in an adversarial state, that was sort of the freedom we gave them, was essentially hallucinate to us where they might be, and they get to pick the worst case, and we're trying to respond to that and go and it's a question of how conservative is our understanding of where they might be and what the effect of their change in location might be and the change in state might be in terms of our actions. Expanding that up to something that's a little more complicated, we're now sort of thinking about the Pong game. And so here you're just sort of trying to, beat the opponent. The point being that, you could take the original, which, does extremely well in terms of the RL agent. It just completely nails the computer. And there's really no uncertainty in the problem. And it's not hard to imagine it's going to win pretty much every time. The point being, if we bring in some type of visual uncertainty, so the RL agent is actually, again, not fully understanding where this wall actually is, and so actually just keeps making mistakes, it ends up being a pretty pathetic game, and it loses really badly. But that is something we can then develop a robustness to, and when we do that, we end up with our robust RL agent now winning 21-10, which is not as good as the one that had perfect knowledge. But on the other hand, if we didn't do any robustness, the computer wins 21-8. So we've been able to reverse the tables and actually get our agent to win, despite having those imperfect measurements that we've introduced and then are accounting for in the uncertainty set. So ultimately, where we want to get this to is to be able to, start flying quads around, maybe, as one example, again, you're doing collision avoidance, you'd like to get to the goal. And ultimately what you do is sort of take that whole MPC you might learn, capture the whole thing as a neural net, and then be implementing that in the feedback loop, where we have sort of some, sensor and process noise being executed on the system in real time. And so we're using this as an example of a system where we're just sort of creating this sort of quite complicated MPC we're trying to implement. Ultimately, what we're trying to do, though, is use this as an example of something we then go through the verification process. And as I mentioned, people have been working on this for some time. Out of George Pappas's group, there's been looking at these semi-definite programming relaxations. They give very tight bounds, but they end up taking quite a bit of time. And so that's this sort of reach SDP down here. So again, runtime numbers here, we're talking about this calculation where, again, ultimately what we're trying to figure out is we start somewhere inside this uncertain set here, can we get to the goal set that's over there? And each of these lines then over on this, shown in this key here, give an indication of sort of at each of these time points, where did that, what type of set was each of these algorithms looking at? And so again, it's pretty good in terms of runtime, not great, but pretty good. The error, though, is quite large. Again, we can partition that and improve the error quite substantially for the reasons I described before. On the other hand, the downside of partitioning is every time you partition, you got to redo the calculation. So the runtime numbers just went sky high. And so that's not a great trade-off. On the other hand, we can go back and instead of using sort of these quadratic approximations, now start thinking about linear approximations, which again was sort of slightly to the left on that bar chart or that sort of spectrum I showed before. So it's faster, more approximate. But the point being that, and that's sort of shown here, that if we go LP instead of SDP, and runtime goes way down, error goes way up. So that's typically a bad trade-off. But now what we do is we bring our partitioning into play and say, okay, runtime's faster. We can afford to run this more times. We can afford to do the partitioning. And when we do that, what we find is that the reach LP here, the partition LP, the runtime has gone down by a factor of 2, but the error has gone down by about a factor of 10. And so it's a much better trade-off in terms of runtime and error. So again, a lot more work to be done here, but this is the beginnings of understanding the trade-offs between sort of, again, SDP, LP type approximations, partitioning, and all those pieces and how they all come together, and then trying to develop better approximations that are fast enough, or faster. Again, 10 seconds is still a bit too slow. It's okay for analysis. It'd be far too slow for any type of a synthesis algorithm. So we need to find ways to speed this up even further, which is one of the other things we're working on. So just touching on some couple of other things we looked at, as I mentioned, we've done the CAD RL, which was thinking about path planning, but that had sort of the RL doing everything. But as is often the case, you think about sort of planning an MPC and using that as a strategy for actually trying to avoid static and dynamic objects. But as you've often seen with MPC, the value of it often depends on the terminal penalty. So one of the things we're looking at in a recent paper, and in fact, it's so recent, I think it's not even come out yet. I think this is ICRA coming up, which is what, this month or next? I'm not sure. And it was actually thinking about the union of those two ideas. So you think about MPC now as the planner, and the cost to go then is actually effectively the deep RL that we looked at before. It's the CAD RL2, the CAD RL, and as the cost to go element. So the point being, the cost to go is is being educated on how to handle these dynamic environments, whereas the MPC is doing the short-term planning, thinking about how to handle some of the collision avoidance for both the dynamic and static obstacles that are nearby. But the point is that we're using the RL to account for interactions with other agents, and this is sort of classic video of just you take 8 objects that are sort of second order unicycles and just sort of turn them on and say go, and as you might expect, they're able to navigate to their goal points quite effectively. So again, this is something we've been looking at for using in the context of pedestrians, in part because they are such complicated things to drive around. They're also sort of planning agents themselves. We don't have a lot of insight to what they're doing, and so we can expect a lot of changes in their behavior. And so thinking about techniques that are able to adapt and avoid them while being safe is important. So again, I've talked quite a bit about this, but within the safe and robust learning, I think, similar, to the paths that we talked about for the robust control from, the 80s and 90s, that, part of this that has to be thought through here is how one describes these real world uncertainties. What is the most effective way to think about what model and perhaps noise uncertainty, is really capturing the unknowns about the world. And then furthermore, how do we embed them in the type of analysis we can do? What I've described is sort of what we can do. The question is that really representative of what's going to happen in the real world? And there are other types of errors and models. The Wesenstein in particular is one that people have been looking at, and as opposed to just these L1 or L2 or whatever type balls that people often think about. And again, there's this distinction between what we can do and what we perhaps should be doing. And I think that needs to be really thought through to try to capture these types of error models. There's always this question when we're doing this learning of just incomplete training data. I think about this sort of Swiss cheese model of N space, where, yeah, I have bits and pieces of data I collected and simulations I did, but what about the rest of the world? And there's this typically giant holes in our understanding of what's actually going on. And if you work with these systems, they're not bad at interpolation, but they're typically horrible at extrapolation. And what you don't want to be doing is to have these things sort of extrapolating, in part because they tend to be very confident in what is the report, and what you want out of these techniques, these types of analysis techniques, is to begin to develop the second flow of information, which says, that might be what the algorithm says, but this is the level of confidence one should really have in what it is that it is reporting, based on how confident we should be based on the training data that this has been supported by. And so I think that whole component there is absolutely necessary to understand how to use these types of systems in the future. So last thing I'll touch on, just do this for maybe 5 or 6 minutes, is multi-agent RL. I mean, again, it's a huge area, but again, everything we've sort of talked about up to now is mostly single agent. There's a lot of key issues as we move forward to multiple agents. And I'll talk about non-stationary in a second, but one of them, of course, typically is what to communicate, who to communicate it with, certainly if you're collaborating, and then ultimately scalability. So these are the 2 key ones I'll talk about here. So the non-stationarity is a classic problem here, which is it's a bugaboo that's been around for quite some time. And it basically just boils down to the point that learning agent thinks that, the world looks like X, but the reality is that it's really a, sort of a world plus, these other learning agents. And the point being that at any given time, learning agents A's view of what learning agent B is going to do is typically incorrect. And the question is, how incorrect is it, and what are the implications of that? And the result is that, what you can find is that it tends to be quite important, with the point being that you'll find these algorithms will often just won't typically converge very well, even to an equilibrium. They might even just diverge, or you might find they converge and then diverge. So that tends to create all kinds of problems when you're learning, really hitting the complexity side of the issue. And the other is that you might just find you convert to a really crummy answer, which is just not typically great. The standard sort of mitigation technique is sort of, what almost everybody uses, which is centralized training with decentralized execution, which sounds great. That doesn't always work. It has its own set of issues. One, it leads to a lot of complexity in the centralized training. Problems tend to get very big and very slow. You don't necessarily get great policies out of that. And that furthermore, it just itself has its own set of issues I'll touch on in a second. Now, within the centralized algorithms, I sort of mentioned this paper here. It sort of does a great job of sort of carving the world up in terms of algorithms that people have been thinking about. We often ended up using QMix. There are quite a few others that the MADDPG is a classic. But there are a bunch of things in here that you might, if you're interested in this field, you might want to take a look at over the spectrum of sort of centralized learning all the way to sort of independent learning. But there's sort of two main, like I said, the MADDPG, the sort of actor-critic type methods, and then the sort of more value-based in terms of QMix that people have been looking at. So again, spectrum of different answers. The challenge, though, is that it's been used and used well and used effectively. But what this centralized sort of learning and then sort of decentralized execution sort of misses still is that it's only considering sort of the current action and policies of the other agents, not the fact that they're continuing to learn and evolve. And so again, you still end up with a non-stationarity issue even in the centralized training process, and that again can lead to the same type of divergence issues that I described before. They tend to be less severe, but they're also still there. And so, again, you might find your learning process does not converge and you're not sure why, and that tends to be one of them. The other issue is scalability, and again, it's unless you have an entire sort of server farm in your backyard, that you'll find these situations or these types of algorithms don't scale well above a set of 10 agents, in part because the joint state action space just scales exponentially with the number of agents. So this sort of more naturally forces you back into thinking about a distributed decentralized computation, and then non-stationarity issues are paramount. And it's sort of, like I say, one of the dominant issues that we've come to face in this field. Now, again, I don't necessarily sort of plan to explain a lot of detail what's going on in this figure, but let's just say that you're an agent up here making a decision with a policy, and you're thinking about sort of a path you're going to take, and other agents are all sort of sitting down here. And ultimately, what this figure is trying to capture in a recent sort of ICML paper of this year, I guess, is trying to capture is degree of sort of forethought that an agent might have in terms of what the impact will be on things I do on say the future. This being the future up here, this being now. And this is sort of Al-Shabadat's paper, and was thinking about one level of interaction shown by the arrows here, and is thinking about, if I do stuff, it will have these implications. I need to take these into account. But what it was missing was perhaps the understanding that the other agents are also learning, and also sort of missing any real interaction between what they may be doing and what the implications would be to us. And so that's what we've added in here, and a lot of these arrows in this figure is trying to capture other types of interactions that the other learning agents in the world may have on us. So what we're trying to think about is how perhaps we should be thinking about interacting with the new learned agents, not just as we understand them now, but how they might be in the future, and what the implications will be for us in terms of this addressing this non-stationarity issue. So what this led to was sort of an ability to be more adaptive and responsive to these other agents, and sort of, a lot of the other algorithms out here, and Lola and Reinforce and Meta PG is, I think, Al-Shabadat's work. And so the Lola and Meta PG are sort of two of the classic ones, more recently been published in this area. And our work that will be at the SML this year is sort of this red line up here. And again, you want to be high reward up here. And so our agents, by being able to anticipate these more interactions with these future learning agents, are then able to anticipate the future better and address this non-stationarity issue. So a lot of detail here. Again, a lot more complexity occurs in the learning itself, but again, it's a case of where does the complexity really bite you? In this case, we're spending more time thinking about what we're doing, but have to do fewer iterations. If you don't address non-stationarity, you can do a lot of iterations and just really get nowhere in terms of conversions anyway. But as I mentioned, sometimes you're forced to go into thinking about decentralization. And when you do that, of course, there's many different ways that one can do it. And typically what it boils down to is what one assumes about everybody else in the world. And the classic is the mean field type of approximation, where you just sort of assume that everyone else is, sort of on average the same, and sort of ignore the deviations. And that tends to scale really well, but on the other hand, can end up being a very crude approximation of the rest of the team or the rest of the environment. So it has good and bad elements to it. And the other part then is thinking about possibly how to communicate and think about who it is that within that group that you might need to communicate. And as I said here, it effectively becomes a learning to communicate problem. And what you're now thinking about is who should I be interacting with and how should I interact with them? And ultimately, that's the type of thing where this ends up having to address. We ended up trying to build on that in work that was in IROS of last year, where we're thinking about sort of trying to learn, sort of recognizing a lot of these interactions between these decentralized agents often end up being sparse. So the classic example given is, think of a soccer field. You might be locally interacting with a couple of players, but everyone else on the field is not that important to you at any given moment. That who's important to you at any given moment might change. So ultimately what you would want is to be able to learn, or recognize that sparsity in the interactions is there, and then learn what type of sparse interactions one should have. And when we did that, we're able to sort of learn better. Ours is the blue up here, doing much better than the other techniques in terms of reward. And then just over here, one of the things we were showing was what was the communication graph that we learned, and we were just showing that we expected it to be sparse, and it ended up being sparse, which was a good thing to see. So again, more detail in the IRS paper itself. So as you can imagine, though, this is just there's many things left to address here. In particular, scalability, in particular, non-stationarity, trying to account for the fact that other agents are learning as well, and try to capture that in the types of policies that one are learning. This is sort of the beginnings of a long trek I think we have to take as a field to find out how to work better in this area. Anyway, so as I mentioned, is work of many players. Most of my postdocs listed here, and the funding agencies. I think hopefully you've seen some examples of some interesting challenges, opportunities, some interesting work that we've done in this area. Again, it's sort of the beginnings of sort of much more work needed. But as I mentioned here in the middle, that as these techniques mature and we begin to think about deployment, I think a lot of emphasis on trust, verification, explainability. These are the key elements that I think are going to be needed in this field. And so if you're getting into it, these are definitely areas to start getting involved in. And I think there's going to be a lot of exciting new work to come up there in the future. Anyway, with that, I'll stop and look forward to your questions. Right.
Thank you. Thank you for a wonderful talk. There's a few questions in the chat. The first question is from Abhilaj Patel, which is for slide 8. It seems that the bidirectional transfer in the case of multi-fidelity RL creates a feedback loop of a different type of signals. Is this the case, and can it cause any convergence issue?
There is a feedback loop, but it's again quite slow, right? None of this is a high band rate, baud rate. So I mean, you're thinking about, it's bidirectional. So you're sort of doing, you'd be thinking in the complex simulation environment about designing experiments. You often do the experiments, and you bring the data back. You can use that to improve the models. You can improve that to sort of understand, the sort of policies and how you might execute them. But it's not really a high, when I think of instability, that's usually going to occur because of a higher rate interaction than this. Like it's unlikely that this interaction is going to go unstable. The stepping up from this simulation environment to the real world. I mean, it's conceivable, an instability would be that you just, are picking the wrong design of experiments. But like I say, this is a slow process as it's typically executed. So I don't think you'd see that type of instability happen.
There's another question also on this part of the talk on the, I guess, on the simulations on the drifting, how to handle the build the robustness in the policy to handle varying surface properties.
Yeah, and you know, you can imagine there's lots of things you could do here, right? And again, I mentioned the work coming out of Stanford where they're actually doing this with real cars. I mean, you know, I think they are addressing, you know, you would have to address a lot more of those robustness questions here. You know, you could imagine that the policy at the beginning was not just, you know, an optimal policy from say LQG or something like that, but something that's more robust to uncertainty in these parameters. The weird part is, of course, that you know, the model of where these magic parameters are and how nonlinear that model is, you know, it sort of shows up in a way that's very complicated to design a controller to handle, right? I mean, so by the time you get to the abstracted model, so the point being you have this very nonlinear simulation with magic parameters in it describing the tire dynamics and the traction, and all of that just gets abstracted down to effectively one number, which is how well is this wheel working. So you can think about an uncertainty in that parameter, right? The traction, and then think about developing control for it. But my challenge to Mark, actually the student at the time, was, you know, no matter how much modeling you do that environment, I'm going to mess it up for you by just throwing more and more dirt on the ground. So I really wanted him to think about that world that he was driving in as being, you know, the representative of you know, is the real world. Think about how best to utilize the data you can collect from it, and not spend too much time modeling it and thinking about robustness. But again, I think, you know, in terms of this picture here, you know, you'd be thinking about robust control here, you know, robust learning and planning here in the complex simulation, such that when you get to the real world, you know, you have sort of a higher probability of success, right? I mean, that's ultimately the sequence you'd want to be thinking about.
And there's one question on the meta learning. How does the task distribution affect the learning of new tasks in meta learning in practice?
How does one do it?
How does the task distribution affect the learning of new tasks in meta learning, meta RL?
Yeah, well, so if the question is how do you develop it, I mean that I think is the entire rub of the situation here, is that that's exactly what you as the designer has to do. Like you don't, like there is no shortcut here. I mean this is like you have to effectively hallucinate what you think the issues are going to be. You know, what challenges do I want to face? So in this simulation here, the challenge they wanted to face was a leg falling off, right? So they went through, and then it's a question of, well, how many legs falling off are we going to account for? And we're going to account for all legs falling off individually. You're going to start thinking about, you know, legs falling off in pairs. And so you can imagine enumerating all the possible issues and situations you might want to handle. And again, you can imagine that gets pretty complicated. I think they only handle single legs here, but this is consistent with a lot of problems one faces when you do any type of robust planning problem or robust control problem as well, is that you have to say, you know, these are the types of uncertainties I think I have. This is the type, how much uncertainty I think I have in each of those parameters. And then you essentially have to enumerate what all those possibilities are, and then think about how one either learns or plans for them. There's no real difference here. The complexity, the challenge here is that the computational complexity goes up quite dramatically with the size of that, of the number of cases you're trying to handle. So you want to be very cautious about bringing in too many things, because you'll find that the complexity goes up in the original learning problem goes up quite a bit.
Sure, thanks. Is there any other questions? Feel free to unmute and directly ask if you.
Can I ask a question?
Sure.
Hi, John. Thank you so much for your great talk. So I have a question about the part that you discussed, the partitioning.
Yeah.
So how does this partitioning in general scale with the dimension of the state space in the worst case?
Yeah, it's a good question. I don't know. And Michael here, he could give you the answer on that. So let me just put that as I actually don't know. I know, I think you've seen some of the other examples we've done, which is slightly higher dimension than 2. But I don't, I can't say offhand what that scaling is. I mean, you can tell that there is a bit of a scaling challenge when you look at sort of how rapidly, the 0.6 became 9.8, in the sense that there are quite a few partitions that were needed even in this case. So I think there, like I said, I'd be hesitant to put a scaling number on that, but at this point.
Yeah, I mean, my initial conjecture is that this would be probably exponential in number of states, and if that's the case, then like one could say, okay, instead of doing partitioning, if the state space dimension is relatively low, let's say up to 5, then I could just grid the space. Probably this is more efficient. I think this is an intelligent way of doing the partitioning, which makes sense. But,
yeah, no, I think, yeah, I mean, this is way better than gridding, because I think the original paper went through and said, look, you could have just done gridding, but this is like intelligent gridding, like you just said. I mean, this is, and yeah, I mean, but again, this is the input space, right? So it's not the state space. So, I mean, we could have many states. What we're partitioning here is the input set, right? So we're trying to understand, so the dimension here of this graph is sort of how many inputs and what type of uncertainty we might considering. So I don't know that you would expect this dimension to be particularly high, right? Because I mean, again, you'd be thinking about the types of noises one might be thinking about, and you could imagine there might be lots. On the other hand, you're probably just looking for the worst ones, right? So you're looking for, what is the worst sensing noise I want to consider? What is the worst, adversarial attack I might want to consider? So, I mean, you don't necessarily need that the sort of the dimensionality of this uncertainty to get enormous to be able to introduce some test of the certification capability. So I agree. The scaling is going to scale, and there'll be a computational problem. The counter to that is you just try to keep the size of this input set as small as practical, while still enable you to do a certification process that's meaningful.
Thank you.
Yeah, thanks. Good question.
Yeah, thank you so much. I guess we are out of time. So let's thank the speaker again. And next week and the week after, we'll have breaks for 2 weeks because of the new RIPS deadlines, but we'll resume afterwards. Let's thank the speaker and see you in 2 weeks.
All right, thank you. Bye, everybody.
Thank you.